All right, so now we're going to go into one of the funner topics, binary search trees, and one of the more interesting data structures, and that's where we're going to end our semester on. We started our semester with binary searching, that pick a number game, and now we're going to talk about binary search trees. We did the 20Q game in class. If you weren't in class, you can look at the video. I'll put it up in a second here for class, and you could play around with it. I'm not going to go over that again. I'm going to dive right into binary search trees and talk about them. So the idea behind binary search trees is, what if as we inserted into the bag, we were also sorting it, okay? And how might that look? Well, binary means that we have these nodes, but these nodes can each have two children, okay? And this tree is this idea that it grows out. So here's a node. It has some data, okay? And it also has a pointer to a left node and a pointer to the right node, okay? And so it's a new type of node. If you compare it to our linked list node, our linked list node just had one pointer to the next node. This is like a pointer to two different nodes, okay? I'm gonna, to be able to differentiate this from the node in linked list, I'm going to call it a BST node. Okay, but if you called it a node, it's no big deal. And you might think of this as some sort of inner class, right? Just like a node was an inner class in our linked list, okay? And you can also think of having a sorted bag just be this binary search tree in the background. Well, let's talk about how this is sorting it, okay? So that's the first thing. What are the rules? Well, the rules are actually kind of simple. You have a number here that's a key, okay? So let's actually just make it your 700 number, okay? So you're a student, all right? In your student class, so you're a student, in your student class, you have your name as one of the private variables, so string name. You have your string major as one of the private variables, and you have your, int credits, int number of credits, right, etc., okay? You probably have double amount owed, okay? And importantly, you have your 700 number. I'm just gonna say 7H number, okay? But that is something we can use as a key, and it's similar to how we picked it out to use it as a key for hashing, because it's a unique number. And so if we have a unique number, and often we do in databases, when you take databases, Professor Gupta or whoever's teaching it is going to tell you about primary keys and the importance of primary keys. That is a unique number given to every entry into your database, okay? And that is actually why we have a 700 number. It's an ID that can uniquely identify you, and we can store it in numerical form in the computer. We can also sort it easy. What do I mean by that? Well, let's say your 700 number. Okay, so I'm gonna reduce the digits of the 700 number. Don't get angry at me. So let's say your 700 number was 19, which is, you can think of 19 as 700000019. Okay, it doesn't matter. Okay, just assume all of that. So it's 19. Okay. Well, what we're gonna say is, so this is the first student, and we insert it into our binary search tree. And how we insert it? Well, we take the student. Okay, and we have the data, so we could write it like this. We have the student, but what we're going to care about is the key, and the key is the 700 number of the student. And so this node, for all intents and purposes, is 19. So student 19 is stored there, okay? And so if you go in here and you look at the data, you'll find the 700 number is 19, and you could also find the name, major, credits, and whatever of this particular student, okay? Now there's two other things here. So we have data, and you might imagine this data is a student, but really it'll be a type T. It'll be something generic so that we can store any type of object in this binary search tree. Okay? And our write node will be, so if this is a BST node, okay, this will be a reference to another BST node, and I'm going to call it write child. And this is a reference to another BST node, and I'll call it left child, or left shark, as Katy Perry would call it. All right, so we've got a right child, and we've got left shark over here, okay? Now, everything on this side has a 700 number that's greater than this 700 number. So everything greater goes to the right. Okay, and I'm going to erase this, but you've done this already. And everything less than goes to the left, okay? Less than that goes to the left, okay? So we talked about this in class, but let's put some numbers in here just to make it. So let's say someone comes in and says, okay, we've got some enrollment right now in the school. So we don't just have student 19, we have student 23. I'm just making these numbers up, so I don't know what's gonna happen. Something like that. Sure. Okay. So 23 is going to be inserted. 23 is greater than 19. It'll be inserted over here. Okay. And anytime you insert, it's going to end up becoming a leaf. Okay. And just for definition purposes, a leaf is a node with no children. A root is a node with no parent. Okay. A binary search tree, so if this is an inner class, a binary search tree, like the head pointer in a linked list, will have a root pointer. So a BST node root pointer. Root reference, okay? And that's how this whole thing will start. So this root reference will reference the first node, and the first node will have two references to two other nodes, and those two nodes could have up to two references to two other nodes, etc., right? Only two references to two other nodes, left and a right node, because it's binary, right? There are, okay, so let's finish this up, and then we'll talk briefly about n-way trees. So we insert 23. 44 is greater than 19, is greater than 23, so 44 is coming off the right of here, 24, 5, 15, 10, 24, 5, 15, 10. So 44 comes up here, 20, oh, was it 22? There's 20 in this too, right? 24 will now, so 24 is greater than 19, greater than 23, less than 44, right? So 24 is here, okay? Notice that 24 is to the right of 23, right? So it's greater than 23 and to the left of 44. So it's in between 23 and 44, all right? 5 would go here, right? 15, well, less than that, but greater than that, so 15 goes here. 10 would go to the left of 15. And 20 would go to the left of 23, okay? greater than 19, but less than 23. All right, so that's what that tree does. And if I messed up by not putting all the values in and when I erased it, I'm sorry. But hopefully that makes sense, right? How this is working. So everything, for every node, if I look to the left of it, all of these values are less, have key values less than my node, okay? And all of these have key values greater than my node, all right? 5, well, to the right is 10, and I know it looks weird, but it's off the right, so 10 is greater than 5, right? If I look at 15, the only thing to the left of it is less than, there's nothing greater than it down here, but there are things greater than it in the binary search tree, right? They're over here. They just all happen to be greater than 19. To get down here, right, you have to be less than 19, right, but greater than 15. All right, so something like 16 would be like less than 19, greater, and would come off the side here. All right. Okay, so that's how we insert into a binary search tree. Okay, that's the rules of the binary search tree, and also how we insert into the binary search tree. We'll talk about how to traverse a binary search tree in the next video, and I'll give you some more definitions, but I don't want to overwhelm you, so I'll see you in the next one.